You already know how a single integral finds the area under a curve. Imagine tracing a line under a hill. You're capturing how tall the hill is, point by point, and sweeping out a region. But now, let's add another direction. Suppose the hill doesn't just rise and fall along one line, but ripples and bends across a whole landscape, like a wavy bathtub floor. A double integral lets us find the volume under this 3D surface. I want you to imagine one thin slice of this 3D shape, parallel to the y-axis. Let's call that our inner integral. It adds up the height across y at some fixed x, so we're building the area of a cross-section. But that's just one slice. The outer integral takes all of those slices and sweeps them across x, adding up every slab to get the total volume. Mathematically, it will look like this, where the inner integral represents the area of one slice, and the outer integral adds up the areas of all of those slices to form a volume. Let's compare aspects of single and double integrals. For single integrals, your input function is going to be something like y equals f of x, a 2D curve. For double integrals, z equals f of x y, which will be a 3D surface. For single integrals, it will be integration over a 1D interval, a to b, on the x-axis. For double integrals, it will be integration over a 2D region, r, in the xy plane. For single integrals, the primary output will be a 2D area, the area between the curve and the x-axis. For double integrals, it will be a 3D volume between the surface and the xy plane. We can compare single integrals to sweeping a vertical line to create a 2D area, and double integrals to sweeping a 2D slice to create a 3D volume. Now that we have the basics, let's work through an example. Recall the differences between the inner integral and the outer integral. Remember, the inner integral represents the height across y at some fixed x. This means we will treat x as a constant, just like we would treat the numbers 1 or 2. Now, we will start integrating our inner integral, treating x as a constant. Important to note, our bounds for this inner integral are y values. After solving for this inner integral treating x as a constant, the outer integral looks just like integrals you have already solved. Once we solve for this, we get our answer to be 1. In our next example, x squared is part of our bounds. This doesn't change anything, as we're still going to treat x as a constant. After doing this, we can solve for our inner integral, which will work out to be 4 minus x squared. After this looks like a familiar integral you've already solved, and eventually works out to be 32 thirds.